Torque. It's more than just a funny word. Today we're going to start with an investigation on balancing things. I have a meter stick here suspended with a fulcrum in the middle, and I put some weights on either side. And you can see that I have extra weight on one side and extra distance on the other. We're going to see if we can't figure out the mathematical pattern between how we can get this thing to balance. Then we're going to use that pattern in order to calculate the mass of an unknown. I have a couple of unknowns here. These things I filled full of sand. So we're going to see if we can't figure out what this unknown is. Now, if you're at home, there's a simulation where you can do something very similar, but the worksheet is pretty self-explanatory. So go ahead, work your way through the first investigation, and when you're done, we'll talk about torque. So torque is known as a rotational force. You have some kind of a lever arm that has a pivot on it. So this thing's going to pivot about this axis of rotation. And what you do is you create a force on this object. Depending upon where you put the force, you're going to actually have more or less torque. If you put a force out here at that radius, you're going to have a lot of torque. If you put the same force in here, it's not going to have as much torque. I have an example of a door that I can show you here. How many of you have done that before? How many of you have gone up to a door, chose the wrong side of the door, and it didn't open? Well, this actually has something to do with torque. If you look at this door is an object at rest. And it's going to stay at rest unless I act upon it with a force. Now, the force I want to act upon it is a force that it makes it rotate. It makes it rotate about this hinge. So we actually have to put a rotational force on this, or a torque. So right now it's not moving. Now it is moving. So it actually accelerated. And in order to do that, you put a force on it. We call it a torque, because this is a force moving it in a circle. So let's look at how we can get it to move. What's this acceleration going to be like? If I put a little bit of force out here with a large radius, I can open the door. If I put that same amount of force over here, it doesn't open the door. You have to put a lot of force on this side of the door in order to get it to move, in order to get the same amount of torque, the same amount of rotational force that will get the same amount of rotational acceleration on the door. So not only is the amount of force that I put, if I put a lot of force, it accelerates fast, or I can put a lot of force over here, it doesn't accelerate as much because radius is also an issue. So we have the force and the radius are an issue in torque. The farther out you have in radius, with the same amount of force, you'd have more torque. The more force you have more torque. Okay? So this is a good example of how torque is used in everyday life. So as you can see, force is important, and so is radius. So the idea of torque, we give torque the variable tau. Do not be confused with the lowercase t. This is the Greek symbol tau, because apparently we ran out of t's. Tau is going to equal force times radius. If you increase the force, you're going to increase the torque. If you increase the radius, you're going to increase the torque. However, there's one more thing that's important. If the direction of the force is also important. So if I pull that direction, I'm going to get some pretty good torque. But what happens if I'm that same radius away, but I pull this way? If I pull out that way, am I going to get any torque at all? No, I'm not. The thing's not going to move. It doesn't, because the pivot is about this point here. So if I pull directly out that way or directly in this way, I'm not going to move at all. So this angle is important. The angle at which you put your torque, in this case 90 degrees. 90 degrees would be maximum torque. 0 or 180 degrees would be 0 torque. So the idea is the angle between the lever arm and the force is important. So we're going to use like a sine cosine kind of thing. So what would it be? Would it be sine or cosine? Well, if we want the sine of 90 is 1, right? That would be maximum torque. And the sine of 180 is 0. So this is actually force times radius times the sine of theta. Now, theta is the angle between the lever arm and the force. So if we pulled out at some kind of a 120 degree angle or a 40 degree angle, then that would, adjust the amount of force that we actually have. Units. Let's talk about units on torque. Force is measured in newtons. Radius is measured in meters. Okay, this is bad. Because a newton times a meter is a joule. This is not a joule. Remember, a joule is work. That's force times distance. And the force and the distance are in the same direction. In this case, remember it's force times distance times the cosine of theta. In this case, the force and the radius are in 90 degree perpendicular to each other. So we got to come up with a different unit. It's not joules. That's weird. Instead of Newton meters, which is a joule, stick with me here, this is measured in meter newtons. I know, it seems like it's the same thing. It kind of is. But you have to remember that the forces are actually perpendicular to each other. It's radius times a perpendicular force, as opposed to both the force and the distance are in the same direction. This is not to be confused with a joule, which is a Newton meter. This is a meter Newton. And I know it sounds weird that that's actually a thing, but it is. There's no special unit for torque. It's meter newtons. A lot of times in cars, you'll hear about foot-pounds. How much foot-pounds of torque they have. Pound being a weight or force, foot being a distance. So in this case, with standard units, we have meter newtons. So let's take a look at an example that we did with the meter stick. So we had a meter stick here, and it pivoted about a point in the center. And we put a weight over here. We're going to ignore the mass of the meter stick. I'm going to show you how we not ignore the mass of the meter stick in a minute, but right now we'll ignore the mass of the meter stick. So let's say we have, half a kilogram over here, and let's put that, 0.25 meters away over there. The question then is, where do we put the, 0.3 kilograms on this side in order to get it to balance? Now, if you look here, what we have is we have two different torques. We have the torque that's trying to get it to rotate this way, and the torque that's trying to get it to rotate this way, clockwise and counterclockwise. And these two have to balance. They have to get in equilibrium if the meter stick's not going to move. So essentially what we have is we have torque 1 from one side plus torque 2 from the other, which is going to be negative, is going to equal 0 because this thing's not going to move. It's kind of like net force. We don't want the net force to be anything if it's going to be in equilibrium. We need to define what's positive and what's negative. Typically we say what's going that way is positive, what's going this way is negative, what's going up is positive, what's going down is negative. Well, with torque, we have to do clockwise, counterclockwise. And I don't actually know if there's any actual conception as to which is which. I think you just need to define it. So for our purposes, let's say that going clockwise this way is positive. So this is positive torque, this is negative torque because it's going counterclockwise. We'll just do that. So that means this side is going to be negative, this side is going to be positive, and then they'll add up to 0. So the negative side, we have 0.5 times 9.8, that's the force, times the distance, which in our case is 0.25. And we're going to call that negative because that's negative torque. It's going around that way. We're going to add to that the torque over here, which would be 0.3 times 9.8 times whatever radius it is, which is what we're trying to find. And this all has to equal 0. So we have torque on one side is equal to torque on the other. We solve this out and we get the radius. This is an example of how we would do it actually with the meter stick. You probably came up with this pattern already, but this shows you how to actually do the math. Now with the meter stick, there's actually something else that's kind of interesting, is the meter stick has weight. It has weight on both sides. So let's talk about how that works. If you look at this meter stick, let's say this is directly in the middle. If that's directly in the middle, the weight of this, the torque from this side of the meter stick and the torque from the other side of the meter stick are going to cancel each other out, so we probably really don't even care. But let's take a look at one where it's not directly in the middle. Let's say we have a meter stick, and let's put the axis of rotation is 0.25 meters on this side, which makes this 0.75 meters. Let's say the mass of our meter stick is 0.2 newtons, or 0.2 kilograms, that's fine. Okay, so you got 0.2 kilogram mass of the meter stick. Let's just take a look at this. Now, if we look at this, this is going to be falling this direction. That's going to fall this direction. Let's say that I have a 0.1 kilogram mass that I'm going to put over here to balance this out. And I want to know, where do I want to put it over here to balance this thing out? How far do I want it from the axis of rotation? A 1 kilogram, or 0.1 kilogram, actually let's go 0.05, make it smaller. Yeah, let's go I'll go 0.1, we'll see what happens, okay? I don't even know if this is going to work, but we'll give it a shot. So let's see here. So I've got, on this side I have to have the torque. So what we're going to use the weight of the meter stick. Now if you think about the weight of the meter stick, over here, how much of it is over here? Well, it'd be 1/4 of 0.2, which is 0.05 kilograms, is how much that, the mass of that. And over here would be 0.15 kilograms. So that's the weights on both sides, or the mass of the meter stick on one side and the mass of the meter stick on the other. So what would we use for the radius on each side in order to get the torque? Well, we're not going to use the full radius of 0.75 here or the full radius of 0.25 because all of the mass isn't on the end. All of the mass isn't over here. The mass is evenly spread out throughout the meter stick. So what we're going to do is we're actually going to use half the distance. It makes sense that half of the mass is in here, half of the mass is over here. So for the distance that we want this meter stick mass to be, we're going to use half of the distance. So over here, we're going to imagine, and this is kind of how I imagine it, is you can imagine the meter stick has no mass, but you're hanging the mass of the meter stick, which is 0.15 kilograms, and you're hanging it halfway, which would be what? 375 meters away, half of the 75. And over here, you can imagine that you're hanging the 0.05 kilograms, and you're hanging that, 0.125 meters away. So these two torques, the torque from this and the torque from this, actually are the torques from the mass of the meter stick. We use this mass, we kind of imagine it as something, just a mass here. This mass is a mass that's kind of hanging that far away. We got a torque here, call that torque 1. We'll call this torque 3, and we're going to add a torque 2 to this side. That's the 1 kilogram that we're going to add over here in order to make this thing work. We're going to call these, since it's going counterclockwise, let's call them negative. We'll call this one positive. So these guys are going to be negative. So my negative torques are going to be 0.05 times 9.8 times 0.125. That's the weight of the meter stick. Okay? I'm going to add that to the thing I'm going to drop. So 0.1 times 9.8 times R. We don't know the distance that I want to put that out there. That's going to, we're going to then, those are all negative. And that's going to, we're going to add onto that the positive one, which is 0.15 times 9.8 times 0.375. So technically, these guys over here are going to equal, and this all equals 0. These guys over here are going to equal this over here. The negative ones, or the counterclockwise ones, are going to equal the clockwise ones. So if I want to simplify this, I can just say that these are going to equal that. I can subtract them to the other side. You can imagine that, which makes this positive. And now I have these negative torques here are going to equal those positive torques over there. And the only variable I don't know is R. The distance that I would hang the 1 kilogram mass, or the 0.1 kilogram mass, in order to make this balance. So this side of the meter stick plus the 0.1 kilogram, 100 grams, is going to balance out the larger weight of the other side of the meter stick. So this is an example of how we would use the weight of the material in our problem. Torque is seen lots of different places, and as you work through the worksheet, you're going to see that there's lots of different applications for where we can use this concept. An example of this is actually your arms. When you lift something, when you lift a weight, that's actually torque. Look at it. My arm is pivoting about my elbow, right? The pivot is right here. Now, there's weight out here. We can ignore, let's kind of ignore the mass of my arm here. Let's say I'm lifting a weight or something. There's mass out here, so we can imagine a torque trying to pull this down. I have to pull it up. How does my arm pull this muscle up? Well, it uses this bicep, right? Now your bicep is actually attached to your forearm here, right here. Now this is kind of a weird thing. Like, it's almost like opening the door right next to the hinge. You're pulling up right next to the hinge in order to get this out here to move. So your bicep is attached maybe 3 centimeters, 4 centimeters away from the actual hinge of your arm. So we can do a problem to figure out, when I lift this thing up, how much force does it take to actually lift it due to the fact that my bicep is connected very close to the hinge. It's actually also interesting that when I lift, if I lift this, if you look at the angle, my bicep right here is almost like 180 degrees. So I can't, if it's pulling straight back, it's not going to get a lot of torque. So it's really hard to lift down here. But once I get to about 90 degrees, then I can lift pretty easily. Like, this part of the lift is actually a much easier lift. That's why when you lift weights, if you've ever tried to lift curls, it's really hard down here, but once you get up here, you can just kind of pump the thing. This is why Bowflex works. Bowflex, what it does, if I lift just regular free weights, I can't lift as much because I have to get through this part of the lift where there's a lot less torque, but until I get to here. But with Bowflex, it uses those arm bands, those like resistance bands, which have a variable resistance. They have a spring constant. So they're actually easier to go down here and harder to go once you lift it to this point. So once you get to here, it actually makes it harder to do. So you can lift more weight with the Bowflex because it lifts it. It's less weight, less weight, less weight, more weight, more weight, more weight once you get here, and you can actually lift more weight. With free weights, you're stuck with the amount of weight you can lift from this angle down here, and it doesn't work as much once your weight gets up here because you don't have as much weight. Very interesting. So that's how kind of those Bowflex and some of those machines actually work. There are lots of applications of torque. You've probably heard of like the Ford F-150, the amount of torque that they have in the tires as the thing goes, because that's how they kind of sell their trucks. So work through the worksheet. There's lots of really good problems with this. This is not the last time we're going to see torque. We're going to come back to it in a couple of days. But for now, see if you can work through this idea of torque, and I'll see you again next time. Thank you so much for watching. If you like science and you like this video, feel free to like this video below and subscribe for future updates.